and ask.
I'm going to push the record now so I don't forget.
Yep, that sounds good.
All right. So 2 minutes after, I'm going to guess that some other folks are going to join us, or I'm hoping that they're going to join us. Welcome, everybody. Look, so good to see everybody. I hope everybody had a really great long Thanksgiving holiday and had time to spend with their families. A quick follow-up from some things that we talked about last meeting. Dave has been working on trying to find us a site to go visit for orphan well plugging. It's kind of a bad time of year and we're having trouble finding a location. So stay tuned. Again, if you are interested, I think I've only heard back from 2 people who are interested in actually seeing how a well is plugged, an orphan well is plugged. So if you are interested, let me know. The second piece, hopefully you all had time to review the list of legislation that NCSL forwarded to all of us. If you had any thoughts about whether that legislation was relevant to any of our discussions or any research that you wanted CSU to look into further, I guess send your comments to me, and or Brooke, would you be an appropriate person to send comments to?
Yes, if I receive any comments, I can bring them back to the CSU group for discussion.
Great. And with that, I want to welcome Lori Tunstall to our meeting. I'm so excited to have her here. She is from the Colorado School of Mines, and I think she's done a lot of work around, well, Lori, I'm just going to let you explain what you've done a lot of work around and what you can share with us today. And she's very interested in making this conversational with Q&A. So, and I think she brought some guests with her today. So with that, I'm going to turn it over to Lori.
Yeah, I was wondering, would it be possible to share my screen? It looks like that's disabled.
Okay.
I've got some slides prepared. But meanwhile, I know Eric might have to kind of join later, but I invited Eric here today. We've been chatting. His company is interested in coming up with solutions for abandoned oil wells that are also environmentally friendly. So Eric, I don't know if you want to introduce yourself any further, but
just a quick sentence. Yeah, Eric Bruzewitz, oil and gas industry my whole career. In the past about 2 years, but really focused on asset retirement in oil and gas, and here in Denver, so focused on a lot of the activities in Colorado as well. So thanks for having me.
Yeah, so his interests seemed too well aligned not to invite him to this group. Okay, perfect. So yeah, I'm an assistant professor at Colorado School of Mines. I've been here, this is my 5th year here in Colorado. I got introduced to this topic in partnership with NREL. They were looking at using biochar, trying to create a market for biochar, which for them was a byproduct from biofuel production. So that's how I got involved in all of this. And we've just had some really great results that I'd be happy to share with you today. We've got several projects going on, so I wanted to kind of just give an overview of some of the work we're doing in this space first. We've got an NSF funded project that's looking at mechanisms for strength improvement in biochar cementitious composites. We are the only group that has been able to replace large percentages of cement with biochar and still see strength improvements. So we're in this interesting position that I've never been in my career, where we've had successes and we don't understand why. So normally research goes the other direction, where nothing works and you're trying to understand why and fix it. In this case, we've had nothing but success, and we don't really understand why. So that project is focused on trying to understand that. Obviously, you want to understand your system so that you understand what could go wrong. So that's what that project is focused on. Then we've got a project funded by Colorado, their Advanced Industries program, that's looking at rheological improvements and also with an eye in sight to developing carbon negative mixes. On the side, we're also looking at early hydration kinetics. So this is kind of relevant for early age properties. So for example, heat output in the mixes and how quickly the cementitious composite sets. So how workable it is for how long. So this is relevant for construction practices, and we're also looking at that. And then we've had lots of questions on economic feasibility as well. So I'll talk a little bit about that. We've done some kind of preliminary analysis, certainly could be more in depth, but just give you a kind of a brief overview of all we're doing in that space. And yes, please do interrupt me if at any time you have any questions. I think that that's helpful. Yeah, Matthew.
Hi, so this is Matthew Warren. I'm the National Oil and Gas Program Lead for BLM. When you guys are looking at this, are you looking at the long-term stability of the biochar in those cements as part of that, or is it all really focused on the initial strengths and build?
Yeah, we're looking at 28-day strengths primarily. We have not looked on the stability of biochar within I'll just call it concrete, right? But what I mean by concrete is any kind of cementitious composite. So cements, mortars, they're all going to kind of behave similarly. So I'll just use concrete as a general term. We haven't looked at biochar stability within concrete, but from other folks who have looked at biochar stability in general, it's incredibly stable. So we don't have any reason to believe that it would be not stable within concrete. If, as we continue doing analysis in this area, if we get some data that suggests that that could be a problem, we'll certainly look into it, but we don't have any reason to believe that it would not be stable within concrete.
So it's not in downhole environments. It's not in a situation. It's not in an environment that would degrade the biochar and leave gaps and pathways in that cement.
We don't think so, though. We don't have any reason to believe that. Certainly that could be tested. We could look at a composite, put it under pressure and see how it behaves. We haven't had reason so far to look at that, but there are experimental methods that we could explore to see if it would degrade. I don't have any reason to believe that it would. The carbon is very stable. It's been treated at a really high temperature. We know that carbon in that form is stable under a lot of conditions. So there's no reason to believe that it would degrade, but certainly that could be part of an experimental program if that becomes relevant for that application.
Okay.
So as I mentioned, our group has had a lot of success with biochar, and that's a little bit in contrast to a lot of the literature out there. Most folks see strength decreases with replacements above, say, 2 to 5% of the cement with biochar. In contrast, we're seeing strength improvements upwards of cement replacements of 15%. This plot here is showing cement replacements with 10% biochar. And so this orange bar here is kind of the range that we see for a control sample, which is in this orange bar here. And you can see here that the biochar mixes either mostly fall within the control sample, so a sample without biochar, or actually exceed it, with the exception of this one sample here to the right, which is an agricultural feedstock, and that performs a little bit worse. But out of the 16 biochars we've studied here, 15 of them behave similarly or better to a control. So like I said, that's great news in terms of application, but we were trying to understand that. We want to make sure that we understand our system so that we can control it and anticipate any adverse interactions. Another aspect of this work, the reason why we're looking at so many biochars, is because we wanted to understand how much variation our process can tolerate. So can we handle various feedstocks, various processing conditions? Do they all behave the same in cementitious systems? So these are all biochar mortars, which I think is, I am not an oil well cement expert. But I believe they're using mortars and not cements. And I think that they call it oil well cements, but it's actually a mortar. So anyway, this should be directly relevant, but we can chat about that more as well. And somebody can correct me if I'm wrong on that.
So Lori, it is a cement. It just doesn't have any aggregate in it.
It doesn't have any sand either?
It depends, but
Okay.
yeah, generally
Okay, so
it's just the Portland cement.
okay, great. So for the strength in cementitious composite, so mortars, the difference between a mortar and aggregate is mortars contains sand, so fine aggregate, and concrete contains sand and coarse aggregate, so like the rocks. And then cement is just the binding material. The great news is that most of the strength in these systems is controlled by the cement phase. So typically the trends that you see in a mortar would also apply for a cement, would also apply for a concrete. There's some exceptions to that, but that's typically the rule. So this is a cement with the sand, but we would anticipate similar trends for just a cement paste.
And then, oh, can we go
Yeah,
back
go
to
ahead.
that?
Yeah.
Okay, so I see that there is only one column that has gasification pyrolysis. Is there a reason why there was only one sample of that? And can we talk a little bit about that?
Sure. Yeah. So far as we've basically just been collecting biochars from producers based on existing processes. So this wasn't something that we designed. We didn't do an experimental design trying to pick a bunch of different pyrolysis conditions. We were just trying to collect as many different biochars as we could. So this is probably not a satisfying answer, but really it's because that's what people have sent us in terms of commercially available processes for the biochar.
Okay, and then when it comes to the biomaterial, I know that there's softwood and hardwood, and we're talking about trees, like as far as pines versus deciduous trees, I'm assuming that that's discounted, that it's more like you said, that, or how it's presented, just how soft the wood is.
Yes. Yeah, there's obviously some nuance there in terms of how that's classified. And
Okay.
if you're interested, I can give you more detail on, what we're counting as softwood. I can go through those individual biochars and see what the sources are. But yeah, we were trying to look for trends to see if there's any issues with various feedstocks. So that's kind of how we grouped them, but there's certainly nuances in how they're categorized.
Great. Thank you.
Yeah, you're welcome. So one thing that is certainly important, and this accounts for some of the strength improvements we've seen. You have to mill the char. If anybody has handled biochar before, you'll know that it's very fragile. You can kind of break it up in your hand. And that's because of this large pore structure here that you can see on the left side. So biochar, before it's milled, looks basically like the biomass. So if you've heated wood chips, then it's going to kind of look like wood chips, but be really fragile. Once you mill this, you get it down to this powdered form, and then it's pretty strong. It doesn't really want to be milled below a certain size. So the milling operation is really brief for what we've done. It's just about 5 minutes. We've primarily used a disc mill. And you get it down to this really fine powder. It's about 10 microns average particle size. It's a pretty, low energy process, given that it's a brief operation. And then that's what we incorporate into our cementitious composites. If you don't do that, you end up retaining a lot of these pores in the cementitious mix. So you can see on the right side, all of the pores retained in a biochar that's not milled. And this doesn't work as well, right? Because air isn't contributing anything to strength. So you're going to see strength decreases. That's really important. And it does account for some of the differences that we see in our group compared to other researchers. But it's certainly not the only difference. We've compared our work. We've tried to copy what some of the other groups do in terms of their processes, and that's just one factor. And we're still trying to understand the rest of the factors. But you can see when the biochar is milled on this left side here, it's really well integrated into the cement hydration products. So that's abbreviated here as CSH. It's calcium silicate hydrate. That's really the glue of the cement that binds everything together. And we haven't seen, when we load the samples to failure, we haven't seen any failures along the biochar line here, like the interface between the cement and biochar, indicating that there's a really tight bond. So that's good news for its use in concrete. So what else is important? As I said, we're trying to understand why our group has been so successful in this compared to others. And we've really approached this from a pretty thorough analysis. We're looking at different pyrolysis processes, the physical characteristics of the biochar, the chemical characteristics of the biochar. And this list is not by any means comprehensive. We have hundreds, if not thousands, of data points for the biochar that we've tested to try to understand what is controlling the strength increases that we observe. Matthew, I saw you popped up. Did you have another question?
Yeah. So as part of this, are you looking at the percent of carbon in that biochar? You know, how close
We
to
are.
100% are you getting? Okay.
Yep. That's part of what we're looking at as well. We have so much data that we've been reluctantly forced to use machine learning techniques to try to process through the data and pull out relevant variables. I'll speak to that a little bit more. I don't want to overstate anything because that's still something we're trying to understand. But it does seem to be that the functional groups on the biochar, including carbon, like the carbon content, is relevant, but not the highest variables. But we're still trying to understand how to do that analysis, considering interplay with the different variables and how that relates to the strength. So it does seem like it's important, not the most important, but we're still trying to understand that. So I don't want to overstate too much on that without having the final analysis done.
Okay. So then I also assume, since you're looking at specifically how pure carbon there is, you're also looking to see what other organics still exist after the process.
We are. So we're looking at some we're considering volatile content. We are looking at functional groups on the biochar itself. That's a little bit more difficult to quantify in terms of, how much is on the surface of each group, because a lot of those techniques just don't lend themselves to quantifying. But we are looking at that as well.
Okay. Are you looking then also at how much of those organics are sugars versus salts?
Correct. Yes.
Okay.
So that has proven to be more challenging. We were hoping for an easier smoking gun. And so we're still parsing through that data to understand how to quantify it and relate it back to our strength metrics. But yes, we are looking at the different speciation.
Okay.
So if you look through literature on biochar cement composites, there's been a couple of mechanisms proposed for how it affects the strength gain. So one is internal curing. Internal curing, the concept behind this is basically you have something inside the mix that takes up water, so it absorbs water, and then it releases it over time as the water is consumed in the cement hydration reaction. So cement hydration, that is what gives us the strength and the binding properties of cement that we think of about cement. So a very important process. Internal curing basically slowly releases the water so that you get a denser microstructure formed in the beginning, but you still get hydration, the full hydration properties. So internal curing is associated with increased strength gains. However, our analyses don't see any correlation with the biochar absorption capacity and strength gains. So we are eliminating that as a mechanism. So again, that's in contrast to what others have speculated in literature, but no other group has done as thorough of an analysis on all of these biochars. So we think that we can eliminate that as a potential effect. Another effect considered is called a filler effect, and this is the idea of when you incorporate small particles into a composite, you get a twofold effect. One, you get a lot of surface area for hydration products to nucleate on. So in other words, you get surfaces that promote growth. And that is typically associated with the surface area of the material. And then another part of this filler effect is efficient shearing. So it basically breaks up the dry cement particles more effectively, increasing the total hydration. Again, we would expect both of these to be both of these kind of effects from the filler effect to be associated with high surface area and particle size and some other effects that we've looked at. None of them correlate with strength gains. So we've also kind of ruled that out. Another thing that has been speculated is, does the biochar act as a pozzolanic material? Depending on the type of biochar you use, you can get varying amounts of carbon and ash. Fly ash might be something you're familiar with that is very beneficial in concrete, that it has a pozzolanic effect, which basically means that it produces more of the calcium silicate hydrate, that glue that ties everything together. However, we've also eliminated that as a potential mechanism. So these are the three kind of predominant mechanisms proposed in literature that suggest, what's happening in the biochar mixes. We've ruled all three of those out in this really thorough investigative program. So now we're exploring two other potential hypotheses. One is calcium carbonate production, which I'll talk about a little bit more in the subsequent slide. And then the other one is is it just strong inert inclusions where you've just got some strong carbon mixed into the cementitious composite, and you're just getting kind of a composite effect. I think that there is less evidence for this last one, particularly since we have some data indicating that we do get a denser final product. So it does seem like there's something else happening that's causing densification, and we just haven't found the smoking gun yet. So I mentioned the calcium carbonate production. This is something that's gotten a lot of attention recently with some of these greener cement technologies like Carbon Cure, for example, that they're promoting the formation of calcium carbonate. So there's lots of data out there indicating that if you can get calcium carbonate growth within a cement mix, you get densification. So it basically fills the pores. We have some preliminary data indicating that we do have carbonate species increased with the production of biochar. But what we're trying to do right now is to understand, is it related to the biochar itself, or is it actually producing calcium carbonate within the mix? So we hadn't done good controls for environmental effects, and we want to understand that better now that we have some data pointing in that direction. So that's work that's still underway. And we are hoping that this is the answer, because everything else we've kind of disproven. But if not, we'll just keep our experimental program and try to understand this a little bit more in depth. Do I have any questions on all of this before I move on to another topic here? All right. So the other thing I wanted to mention, one of the challenges with using biochar in concrete mixes is rheology. So rheology is basically how well does the material flow, and it's relevant for construction applications. How easy is it to place? At high biochar loadings, so the video I'm going to show here is at 15% cement replacement, we get some strange behavior. And this is the reason why we proposed to study this and develop solutions for this with the state of Colorado funding that I had mentioned. So if you look at this, you can see just how stiff these mixes get. So, right, this is not typical kind of concrete behavior. Typically, you can just pour it out, right? In this case, it's acting more like kinetic sand. There's a special term for this. The material tends to be shear thinning and shear thickening. So the interesting thing is that when you apply a little bit of vibration to it, the material flows. So this is a vibration table. So you can see that it flows really nicely. Now, again, I am not an oil well expert, but I imagine that some of this could be beneficial or particularly helpful in that environment where you have steel caissons and you can apply perhaps vibration to it and get the material to flow. So I think for this application, it actually might not necessarily be a bad thing, and you could increase the loadings. Right now, for us, this has been a limiting factor for how much of the biochar we can incorporate into the mix, because at a certain loading, you get this kind of strange property, which doesn't work well for typical construction placement. Yeah, Matthew, do you have a comment on that?
Yeah, so when we talk about oil well cementing, you're gonna be trying to pump this through a 1 or a 2 inch piece of pipe at depths of up to 15, 20,000 feet.
Yeah.
And the video that you show there, you absolutely would not be able to use that consistency for that type of plugging. And because of those depths, there's no way to vibrate that casing.
Okay.
Especially because a lot of times that casing does have cement from the primary cementing operation on the backside, which would
Yeah.
reduce the effect of that vibration anyway.
Yeah.
So
Okay.
you're gonna have to keep this to where you can pump it through some fairly small sizes at some fairly long distances.
Yep. So I will say at lower biochar loadings, you get conventional behavior. So it's only
Yeah.
at these higher biochar loadings where we have a problem. And so for our interest, because we're really looking to get to carbon negative mixes, for our interest, we're trying to solve the problem with higher biochar loading so that we can get that carbon neutrality or even negativity in these mixes. But any amount that you incorporate has an environmental benefit. So at 5 to 10%, you get very conventional behavior, and you still get an environmental benefit, but not quite, neutral or negative, which is what we're targeting.
Right.
But that's good to know for that application. I was kind of hoping that perhaps we could get around that then, but it seems not.
Lori, can I clarify what I think I heard you say, which is part of your research is to try to figure out how you make the cement itself carbon neutral, so that the production obviously has some producing or creating or making cement has emissions problems or what, sorry. And so you're trying to add enough biochar to offset the production of the cement itself.
Correct. So we're really looking at concrete as a composite, so the whole kind of mix. So by using less cement, which is the biggest CO2 emitter in concrete, and then by replacing the cement with a carbon negative material like biochar, we get a dual benefit of using less cement, incorporating a carbon negative material, and then depending on your mix design, you can feasibly get to carbon neutral or carbon negative.
But the more that you add, the more thick this gets, and like kids playing with that sand.
Correct.
Yeah. Okay.
Yeah. So that's
for those of us who are high level.
Yeah. Now, so I'll say several things to this. There's chemical admixtures that are used in concrete to offset these effects. However, none of them are designed for use with biochar because this is a new material. So there's a lot of potential solutions to this. One is specialized chemical admixture design. Another is tuning the mix to use fly ash, which already has kind of a lubricating effect because of the spherical particles. So we're really approaching this challenge from a lot of different directions. But yes, we would like to kick it up more and have it still be, a conventionally placed mix. Right now, this is obviously not something that you could use on a construction site, right? So that's the challenge for this Colorado sponsored project, is to solve this problem.
Awesome. You've got some hands up, Laura, so I'll let you drive that.
Yep, that sounds good. Brooke, I think you were first.
Yeah, hi Lori. I was wondering, what was the max percent you could do replacement with biochar and still see conventional behavior?
10%. Well, so I'll say we haven't looked at the window between 10 and 15. 10 works, 15 you get this. So we're trying to understand this more systematically by employing some advanced rheological testing. From rheology experts we've chatted with, it seems like the problem we're having is just a lot of small particle packing. So that very typically shows this kind of behavior. So we should be able to tune it and get a more refined number. But right now, from kind of a bulk test, we've tested 10%, that works, 15%, you get this. So somewhere within that range. Is it Carmia?
Yes. Hi, and I'm with the BLM.
Okay.
So you may have said this, but when did you mix this? Was it right before whoever grabbed a handful of it and placed it on
Yes.
the vibrating table. Okay, so you see that effect immediately.
Yeah, so
pretty
this is
much.
the mixing bowl. So this was just kind of mixed. We use like a KitchenAid mixer to make small batches. And then
Okay,
immediately, as soon as it doesn't have a shear applied to it, it stiffens. So it'll mix in the mixer because you have got like a certain shear rate that's applied, and it'll mix kind of normally. But then when you don't have the shear applied, and so then you can also see when the vibration table goes on, you've got another shear effect. And when it has a certain shear rate, it'll flow. My expertise is not in rheology, but we've been working with folks that are experts in this area, and apparently that's kind of typical behavior of like high particle loaded materials. And so you get the shear thinning and shear thickening kind of effect. And so yeah, it's a really interesting challenge I've never seen with cementitious composites. But I think there are several potential solutions for it. We just have to kind of develop something for the specific new mix that others haven't really played around with before.
And Lori, your video looks the way that appears to work looks the same as when you have high salt levels in your mix water. I'm talking like 20% or saturated type levels with your mix water. When you add it to your cement, it thickens up just like that.
Oh, cool. That's interesting. I didn't know that. Yeah, we'll explore that. That's very interesting.
And that's just regular sodium chloride salt, not like some of the other salts.
Yeah, that's really neat. I've never heard that before. So,
And then for folks who are putting stuff in the chat, Lori, maybe we'll try to get to the chat at the end.
oh, that sounds good. Thank you. I was not paying attention to the chat. Okay. So we're also looking at early age behavior. This is just work that's been done in the last month. So pretty preliminary, and we only have looked at one of the biochar samples out of the 16 so far. We do see some set time delays with inclusion of biochar. So in this top plot here, we go from 2, 5, and 10% from the red, blue, and yellow curves. And so you can see that our initial set time increases with the inclusion of biochar. Again, there's some strategies that you can use, like chemical admixtures, that can offset this. We haven't played around with that yet. We're just trying to understand what do we need to control with these mixes. So you do see some increased set time. You also see slightly decreased heat output from these samples, and we're trying to understand why there. So that's kind of all preliminary results, but I just wanted to mention that that's some work we have going on as well.
So a question for you, Lori, on the setting time, is that what you would call the gel strength, where it supports itself, but may not be fully set?
Correct.
Okay.
Yep. So the initial set time is, exactly what you just said.
Okay.
And then final set time is when you get like hardening, where,
Okay.
at least on the surface, you can't really penetrate.
Okay.
Okay, so I wanted to talk about some paths to net zero. We have more work going on with this that is really promising, but I've just kind of outlined some basic mixes where from, a basic carbon footprint analysis, you could get to carbon negativity. So, excuse me, we've got these two top samples are the ones that we've focused on most for this presentation. So those 10% mixes, we estimate a carbon footprint offset of about 32%. And those are the ones that behave really conventionally and have similar or improved strengths. I've got a little in-person sample too, so you can maybe get a better impression of what this looks like. This is 15% replacement of cement with biochar. And so we've demonstrated that works in terms of strength improvements, pretty similar behavior, except, some early age differences. But we also want to explore getting to carbon neutral or carbon negative. And so if you look at this bottom row here, this is just one potential path forward. So say we can't maybe get to, really large replacements of the cement with biochar. But if we partially replace it with biochar and fly ash, then we could get to a carbon negative mix. And like I said, when you include fly ash, you get that lubricating effect. So we anticipate that we won't have the same kind of rheological challenges as just replacing the cement with biochar. However, we'll see how that works out. That's stuff that we haven't explored yet. But I just wanted to kind of indicate a path forward with biochar as part of the solution where we could really feasibly get to carbon neutral or negative. We have done some analysis with biochar samples, biochar and fly ash, excuse me. So if you look at this plot, I'll just give kind of a brief overview of how to interpret this. The gray is the control. All of the bars here with the dots are mixes that include biochar, 10% biochar replacement with the cement. And so and then the yellow, the light yellow is with 20% fly ash, also replacing the cement. And then the gold color is 30% fly ash. So if we kind of look from left to right, focusing on this 28-day strength, we can see with the biochar, we've got kind of comparable to the control when we just have the biochar. And then when we include fly ash and no biochar, we see a pretty significant strength reduction at 28 days. And this is typical for fly ash. Fly ash, you get benefits at later ages. 28-day strength is often lower with fly ash mixes. However, if you include both fly ash and biochar, you get increased 28-day strength compared to just the fly ash alone. And we would anticipate that you would get further strength improvements at, say, 56 days, which is typical for fly ash mixes. So this is kind of just demonstrating feasibility. This mix here on the bottom, the 30% fly ash, 10% char, that would be associated with a 61% offset in carbon footprint. So, just kind of pushing the boundaries here and trying to get to better and better for carbon neutrality in these mixes. Also just a quick kind of, I just realized, I have this is not correct numbers. I can get you these numbers. I gave a presentation in Mexico recently and converted this all to pesos. And so this is in pesos per kilogram here in the actual plot. I only changed the top bar here. So I can get you those numbers, except the furthermost right column is correct. So cost compared to the base is still accurate. So we have done some preliminary analysis based on OPC cost, fly ash cost, and then biochar, which ranges quite a bit. So depending on the biochar cost, we could get to cost parity for some of these carbon negative mixes, or cost parity or better. So there is potential here for this not only to be a green solution, but also an economic solution. And that's one of the big driving factors for us from folks that we've talked to. Everybody wants a green solution, but it really needs to make sense economically in the current market without a lot of carbon credits and carbon taxes and such. Those are coming, but in the current market, people really need a solution that's economically similar or better than the current solutions. And so that's one of the things that we wanted to understand, to see if this has the potential, and it certainly does if you look at these numbers. And again, you could do the math here. So this is not written correctly here inside the actual table, but I'm happy to get you those numbers as an update.
Oh, so question on that.
Sure.
Going back to it, because so much of the carbon credit and then just the cost is where you're sourcing materials from. So when it comes to the biochar and the fly ash, is it local, or are you having to get it from far away?
Yeah, great question. So I'm basing the fly ash cost. I'm not considering transportation cost in this analysis. It's a very kind of rudimentary analysis. not considering transportation costs. Fly ash, these are numbers that for wherever, say, like ready mix suppliers are able to get their fly ash, this is the estimate that they use. So assuming typically that they only are going to use local sources, so that probably is based on a local source. I'm not sure how that would change with transportation costs. Typically in the ready mix world, if it's far away, nobody's going to use it because it's just prohibitive. For the biochar, biochar producers are popping up everywhere, but finding local producers now might be a challenge depending on where the ready mix suppliers are. There is a big ready mix, there is a big biochar producer in Berthoud, Colorado that we've tested. And so they are on the lower cost side as well. So not considering transportation costs, they would probably be on this lower cost side. But it's not considering transportation costs. It's not considering the increased costs. This should be minor, but like milling costs for the biochar. It's also on the positive side, it's also not considering the changes in batch volume. So since biochar is lower density, we actually get a higher volume yield. And we really need to adjust these numbers based on the final yield versus the starting kind of masses that we're using. So I've been encouraging my students to actually measure the volume they're producing. We don't have all that data yet, but when we do, we'll adjust this as well to reflect that. Yeah, Matthew, did you have a question?
So yeah, one of the things, you're starting with a control on your cement, and I didn't see it in your presentations. Maybe you mentioned it and I didn't catch it, but what class of cement are you starting with? Just because of
it's
the
a
different
type 1, 2.
type 1, 2.
It's a
Okay.
type 1, 2 cement. Yeah. And we do need to start adjusting now that everything has kind of shifted to the type 1L. We do need to look at that and make sure that everything kind of works similarly. This work started before that switched over. So we'll need to look at that. But yeah, this is all based on type 1, 2.
Okay. And the type 1L isn't currently used for oil well plugging on federal lands.
Okay.
Because of some of the setting properties and stuff, issues that we're having with it, from what we've seen.
Okay. Yeah, that's great to know.
And so there is a difference when it comes to actual manufacture of the cements. And so I know there's a lot of cement manufacturers that will make stuff for like ready mix and construction type cement, but they won't make those oil well cements because they have to retool their entire operations in order to make those oil well cements.
Interesting. Yeah, and we would be happy to look at if that's something you have access to and could send us, we'd be happy to look at how it behaves with oil well cements. That's
The type 1, the type 1, 2 is going to be pretty close.
Okay.
But the type IL is not.
Okay. Yeah. Yep. This is all type 1, 2. And as I said, most of our work is really looking for conventional construction practices. So we'll want to look at type 1L. But we're really happy to look at this and approach it in a lot of different ways based on. Oh, I muted myself. Sorry. What's relevant to industrial practice. So our research group, loves to understand the fundamental science, but always with line of sight to application. So we want to understand it so much as it helps us to improve application. So if there's anything, relevant for specific applications, we're always happy to look at that. And we appreciate the input from others who are more active in those spaces than we are as an academic lab. Yeah, so that's really all I have, just to kind of summarize the work we're doing. We've tested 15 out of 6 we've tested 16 biochars, and 15 of them worked similarly to the control. Strength improvement mechanisms are still not well understood, but we do see strength improvements very consistently, and we're working to understand that better. We're also working to improve the rheology of the mixes at those higher loadings. We're seeing some set time delays as kind of preliminary results, and we're trying to understand why that is and if we can control that using some chemical admixture design. And then for us, most importantly, just demonstrating that a carbon negative solution is feasible using this technology, and it's something that has the potential to be implemented pretty soon because it's at cost parity. So we really anticipate that this is going to be something we'll see a lot more of. We're seeing a lot of research pop up in this area, a lot of interest from ready mix suppliers. So I think that this is going to be something that we hear a lot more about in subsequent years, and we want to be ready for it and understand what the implications are. I am going to switch over to chats here. I'll start from the beginning. Okay, that's a question for Matt. Yeah, so temperature profiles, that would be certainly interesting. If this is something that has potential for oil well applications, I'd be happy to chat more about what are the relevant conditions that we need to explore to see if this is feasible and how things change.
And
Well, and
just
along
to
those lines,
Yeah.
when it comes to plugging operations, generally we're going to be plugging from about 40 below ambient temperature at surface to over 100 degrees, 110, 115 degrees on a bad day. And so some of those things that also go into play is going to be the temperature of that mix water. But then, so that's at surface, but then you're going to have temperatures that range from that same surface temperature to 250, maybe 300 degrees. In some cases where they actually do steam flooding, you can see much higher bottom hole temperatures. So it's a much wider range than what you would generally see in construction.
Okay. And are you giving these numbers in Celsius or Fahrenheit?
Fahrenheit.
Okay, I assumed.
Yeah. I could convert to Celsius, but we generally deal in Fahrenheit.
Yep, that's perfect. I just wanted to make sure if we do go into that area, what's the relevant temperatures. Okay, so let's see.
and to go with that, I mean, when we're talking downhole, we're dealing with more pressures, which I know pressure is a lot of, one of the main variables that you've been considering throughout all of this. And then water, when it comes to plugging too, right? We're trying to isolate that well bore from any formations that contain water.
Yeah.
So how does it react with that? And then I know one of the big things is also I guess just the organics, right? And the generation of, well, even like H2S, right? So how it reacts to different chemicals and organics, really.
Okay.
It sounds
Yeah,
like it's fairly inert, but good to know.
Yeah, I think it so far from everything we've tested, it seems to be inert in the at least in terms of reactivity in cement. However, there are some things like the change in set time is most likely due to some sort of chemical like a chemical process that it's delaying. So we want to understand that better. I think a lot of this is preliminary data that biochar is relatively new for use in concrete. So trying to understand, trying to know what we don't know basically right now. So I think those are all great things. I will say from what we've studied, it does densify the concrete. So in terms of permeability, we would expect it to be less permeable than a conventional mix with the biochar. And as I hopefully made clear, we're still not really sure why. Every hypothesis we've tested so far, we've disproven. So we still want to understand that. And I think especially for these more specialized applications, I think it is important to understand what are the limitations of our understanding of this process right now, and how could that potentially affect a specialized application? For conventional application, if we don't have all the answers, but we know that it's consistently improving the strength and we know what to anticipate for early age properties, then it's probably sufficient. But for some of these specialized applications where it's really critical to make sure that we understand its performance, I think we have some more specific analysis to do.
Lori, do you mind unsharing your screen
Sure.
so we can see all each other?
Yep.
So I'm just wondering if folks then want to put this in a higher context of the advisory group, and based on Lori's presentation, I feel like we have some questions that still need to get answered as part of, can we use biochar in cement for plugging wells? Simple Karen, high level elevator discussion, right? And so I think I've heard maybe the conditions that School of Mines has been looking at have not been the same conditions that we would see underground, under different kinds of pressure, temperatures. And those are some questions that would need to get answered as part of any like research. Is that appropriate? Am I on the right track here? I'm just trying to like give us some direction. So as we're working with CSU, and I know that somewhere down the line, if we're going to be making a recommendation about, let's do a pilot, or what has to get answered, what are some things we want to put forth here to CSU, because they're a part of the conversation here too. I want to make sure that those get addressed in the report that we put together. So do folks want to kind of put some ideas out there and make sure that we're all on the same page?
So when it comes to, at least on the BLM standpoint, in order for us to think about using a biochar type cement, we're going to compare that to the relevant API standards. So American Petroleum Institute, they have standards on cement manufacturing and properties of cements and all of that goes into that. And so we would be comparing against those standards, because that's what we use for our oil well cements. And so that would be a good thing to make sure that we're incorporating, hey, how do these reactions compare to these standards, and how API came up with developing those properties.
Holly. And Holly and Matt, Holly's been trying to figure out how to get in touch with you. So now you two are connected kind of, and I want to make sure that you two have indeed connected now that I see you both on the same page.
Yes, I would love to maybe get your email address so I can follow up with some things, including like just what those specific standards are, so that as we're putting together some of our testing, we can make sure that we're using the right ones, because I've seen a couple of different organizations with different standards, and I just want to make sure we're using the right ones for you all. Thanks.
And I put my email in the chat.
Dave, I saw you.
Yeah, I'll just echo Matthew on API standards. I mean, that's really what I think the state would be looking for like a full-scale implementation of this. I'm not the engineering manager, but I'm guessing that she would probably agree with that.
Is there like a certain range within, like, obviously there's a standard to be met, but like when we're comparing the cement to like the neat cement to the biochar cement, is there a certain window of variability which is acceptable?
Well, the state has rules on what's required for cementing and plugging in particular, and I'm guessing BLM also has the same thing in an onshore order.
Correct.
And Dave, are those in our rules? I just want to make sure that we're like, instead of just saying it's out there, like how
Yeah, I'll
people to the right place. So could
I'll try and get it in the chat in a second here.
Great. And then is it easy for the BLM folks, is there an easy spot to point CSU to in your rules and what you're looking for and require?
Yeah, it's in so it used to be an onshore order. We've recently modified them. Well, we codified them in the federal regulations. So I'll get a link to that and put it in the chat.
Thank you. Anything else for Lori? This was like so informative. I feel really helpful.
I saw in a question from Stephen Arouza that I'm not sure was answered. So about the milling process and if there's a detrimental effect on the ability of it to capture rogue hydrocarbon emissions.
So I'm not familiar with hydrocarbon adsorption and what the pore size. So you still have all the nanopores, which is typically where adsorption occurs in my experience. I'm not familiar specifically with hydrocarbon emissions, so someone can correct me if I'm wrong on that. We're really just getting rid of the macropores, and usually macropores are not so great at adsorption. So correct me if I'm wrong in terms of the application for hydrocarbons. But all of the other the nanopores still exist, and I know that typically for sorption properties, that's where that's controlled.
And at least for downhole plugging, cement isn't going to be the only barrier that we use. We're using more and more mechanical isolations as well. So you have that, and so the cement isn't so much of an absorption of the hydrocarbons as much it is just a physical barrier.
Did I clarify what I think I heard Lori say? Because I'm not sure I quite understood. When we mill down the biochar, Stephen, I don't want to put words in your mouth, so I'm trying to understand your question. Sorry. It's the group has been thinking about biochar in two ways. One, which is carbon capture or carbon credits, and the other is its ability to potentially capture hydrocarbons if there were to be a leak, and it's beneficial. Maybe it's beneficial use downhole in cement as a capture opportunity. And did I hear you say, Lori, that if you mill it, then there's smaller particles and its ability to absorb hydrocarbons might be lessened? I'm trying to think of a high level way to say what we're asking or what the answer is.
I honestly am not familiar enough to say that
Okay.
one way or the other, but typically that it wouldn't matter, because typically absorption is controlled by the really tiny pores that still exist. So I would anticipate it would be fine, but I would need to look into the literature a little bit about that to see if others have studied which pore sizes control that. But typically it's the smallest pores that control adsorption.
Okay,
And
so
those would stay.
What I just said. Okay,
Yes.
got it. Thank you so much. And Stephen, I'm sorry, I'm not trying to put words in your mouth, but you're being kind of quiet, so I'm trying to figure out what you were asking and what the answer was.
No, I really appreciate that. Thank you.
Okay.
And then generally speaking, it just creates the greater the surface area, the more potential for absorption too, I imagine.
Yeah, these are still, when we mill them, we have huge surface area. I mean, it's upwards of 200 meters squared per gram. So I would not anticipate any issues with adsorption of hydrocarbons. But as Matthew said, that it probably wouldn't function in that role anyway, because it would be bound up in the cements. So it would be more of a barrier than a sorbent.
Okay, we're at our time, so I just want to make sure we thank Lori. Thank you. So helpful. Any other questions for her before we go? And CSU, do you feel like you've gotten what you've needed from Lori and the advisory group?
Yeah, I think so. That was very informative and really exciting to listen to. So thank you.
Yeah, I'll put my email in the chat as well. So if there's any follow-up, I'd be happy to chat more and collaborate on this topic. So feel free to reach out.
Thanks everyone for their time today. Have a great day.
Sorry.
Thanks all.
Thank you.